Hi, I'm Steve Mann and this is Paper Classroom. Welcome to another one of our science tutorials. In this particular tutorial, we're going to be talking about atoms, electrons and shells. This is really a two-part tutorial. In the next video, I'll be talking in depth more about electrons and their behaviour within the shells, but this is just a general tutorial about the influence electrons have. So to begin with, this as we know it is an atom. We said that an atom has a nucleus, and around the centre of the atom, around the nucleus, we have these a set of shells where all the electrons reside. For the moment, I've just done this sort of fuzzy area to say all the shells are really there. It's unimportant for what I want to talk about. What I pointed out also is that there are a certain number of protons in the nucleus, and there are an equal number of electrons orbiting the nucleus. So an atom is electrically neutral. That's the first thing to note. If it's electrically neutral, it's an atom. If it's not electrically neutral, it's not an atom. We give it another name. If, for example, we take more or more than one electrons away from the atom, then we still have the same number of protons, but we now have fewer electrons, and therefore the atom now has a positive charge. So because it has a positive charge, we no longer call it an atom, we call it an ion. And to differentiate whether it's positively charged ion or a negatively charged ion, we actually call it a cation. We call it a cation because it is cathode seeking. It's attracted to negative things. Similarly, if we manage to push some electrons into that electron cloud around our atom, the atom now has more electrons than protons. So again, it no longer is electrically neutral. It has a negative charge. So because it has a negative charge, again, we call it an ion. And to be more specific, we call it an anion. Anion because it's attracted to the anode. It's attracted to something positive because itself is negative. So hopefully that makes sense. If it's electrically neutral, it's an atom. If it has a charge on it, it's no longer an atom, it's an ion. If it's positively charged, it is a cation. And if it's negatively charged, it's an anion. So let's move on to shells now. What do we mean by shells? Well, if you remember, Rutherford was the first one to propose that the electrons were orbiting the nucleus, and he said they did it just randomly. And it was Bohr later on who came along and said, no, the electrons are orbiting the nucleus, but they're in very, very specific orbits, or a range of orbits that we call a shell. And these shells are given letters to identify them, K, L, M, N. You could, if you wish, called it the first shell, the second shell, the third shell, the fourth shell, but traditionally they've been given these letters K, L, M, N. K shell is nearest the nucleus, N in this diagram is further away, but there are other shells beyond that. I've just stopped at 4. We'll put that to one side for a moment and look at these. These are called the magic numbers, and those numbers refer to the number of valence electrons in the relevant shells. So they're called magic numbers because that's the number that the atom is trying to achieve. So in this very first shell here, it wants to have 2 electrons, not 1, not more than 2. It wants to have 2. This second shell, the L shell, it wants to have a maximum of 8 electrons. In the third shell, it could hold more, it could hold 18, but it wants to have 8. And in the fourth shell, it wants to have 18. There are actually more than 18, but it wants to have 18. And I'll talk about where these numbers come from later. So those are what we call the magic numbers. There's also this formula, and this formula tells us what the maximum number of electrons there are in a particular shell. So the magic number is how many valence electrons the atom wants to have. This formula tells us the maximum number, which is often more than what valency requires. So the formula is 2n squared, where n refers to the shell number. So in this case, in the first shell, n is 1. So if we replace n by 1, we get this, 2 equals 1 squared. 1 squared is still 1. 2 times 1 is 2. So the maximum number of electrons you're allowed in the K shell is 2. If we move on to the L shell now, this is the second shell. So now n equals 2. So we simply replace this n by the number 2, and we get 2 times 2 squared. 2 squared is 4. 2 times 4 is 8. So the L shell can hold a maximum of 8 electrons, no more. If we move along to the third shell now, the M shell, so now 1, 2, 3, n equals 3, n squared, 3 squared, so 2 times 3 squared, 3 squared is 9, 2 times 9 is 18. So in this third shell, we can have a maximum of 18 electrons, but under our magic number system, we want 8 to give it the optimum valency. And finally, in this example, I'm going to stop at n, but remember there are more shells beyond this. In the n shell, 1, 2, 3, 4, n equals 4. So 2 times n squared, we've said n is 4, so 2 times 4 squared. 4 squared is 16, times 2 is 32. So in the n shell, we could have a maximum of 32 electrons. In actual fact, the number of valence electrons we want is 18, and that's the fourth magic number, 2, 8, 8, 18. So I hope that's all made sense to you. Thank you very much for watching this video. Please enjoy our other videos and feel free to give us any feedback that you wish.